Hello friends, in previous lecture we have studied in detail the SN1 and SN2 reaction with its mechanism, as well as we have studied the SNI reaction also. Now today we are going to discuss the nucleophilic substitution reaction with aryl halides or haloarenes. Now haloarenes are nothing but a substituted aromatic compound, halogen substituted aromatic compound. You can have the example like chlorobenzene, iodobenzene, bromobenzene. So here you can see the structure of that, where halogen is directly attached to the aromatic ring. This is what a chlorobenzene. Now we are talking about the nucleophilic substitution reaction. The first question, whether the nucleophilic substitution reaction is possible or not. So yes, for haloarenes, the nucleophilic substitution reactions are possible, but there are certain conditions that nucleophilic substitution reactions are possible under drastic condition like high temperature and pressure. Before that, in previous lecture, we have studied the SN1 reaction and SN2 reaction for alkyl halide. Now the same type of the reactions are possible or not for the haloarenes. So we'll talk about SN1 reaction and SN2 reaction for haloarenes. So now if you ask the question whether this SN1 and SN2 reaction as far as the haloarenes are concerned, whether it is possible or not, the answer is no. That haloarenes doesn't undergo nucleophilic substitution unimolecular reaction or doesn't undergo SN2 type of the reaction. Now it has two reasons. Now here we will consider what are those reasons why the haloarenes doesn't undergo SN1 reaction or SN2 reaction. Now in SN1 reaction, we have studied it is a two-step reaction where there is a formation of the carbocation. And second step is the nucleophilic attack on that particular carbocation. Now you just see the structure of chlorobenzene. Now, if chlorobenzene shows SN1 reaction, it should dissociate to form a phenylcation and chloride ion as a Cl minus. But when you see the resonating structure, that this shows the resonating structure, that is positive R effect you can consider. So here it is double bond Cl, negative charge at ortho position, and chlorine will get a positive charge. And no doubt this corresponding negatively charged species gets stabilized by various resonating structure. Now here you will observe this CCl single bond, and due to resonance, this CCl becomes a double bond. So in the double bond character, the strength of the bond is high, and that's why even the bond length is correspondingly less. And that's why the energy required for the breaking of the CCl bond will be correspondingly high. And that's why this chlorobenzene cannot dissociate easily, providing a phenylcation and chloride ion. This is what the first reason. Due to this double bond character of CCl bond, the bond strength becomes more, and that's why the easy dissociation is not possible. This is what the first reason we consider why the haloarenes doesn't undergo SN1 reaction. Now second, SN2, whether the haloarene shows the SN2 type of the reaction or not. In alkyl halide, we have studied in SN2 reaction, there is a backside attack of the nucleophile. Now when you see the structure of the haloarenes, where the chlorine attached to this particular carbon, this backside is getting blocked by this ring system. And that's why the incoming nucleophile doesn't attack on this particular carbon from backside. And that's why the haloarenes doesn't undergo SN2 type of the reaction. This is what the second reason why the haloarenes doesn't undergo SN2 type of the reaction. No doubt, but the haloarene shows the nucleophilic substitution reactions under drastic conditions only. I already mentioned at high temperature and high pressure.